is Alicia Hernandez, and I am here with my friend George.
Hello.
Yeah, he's from education major, and I am going to teach him Gauss law. So can I ask you for a few minutes to explain to you this?
Yes, of course.
All right, thank you. All right, so first I would like to tell you a little bit about Gauss law, right? Which is an equation that relates the amount of charge inside of a closed surface through the amount of electric flux through a surface, right? So as you can see here, right, we have the equation for that one. So this kind means the net flux, and this is the E with the total of charge enclosed by the closed surface. This is divided by the epsilon naught. So, but this is the general formula. The second one is the one that we mostly use. So, for the closed surface, right? So we will have that, you know, this one, then the next flux times the electric fields times the dA, which is tested by Gaussian surface. So everything that we want to know is the total charge enclosed over epsilon naught, right? So this can have to obey two rules or two conditions. The first one is that the electric field has to be constant on the surface, and the second one is that the electric field is parallel to n hat or the surface, or it can be the angle between electric field and the n hat equal to 0, right? So if we test this one, as we see here, right? If you have a point charge here, right, and then you want to test that one with the Gauss law, right? So you go around, you know, the charge, you know, with the surface here, and then you will see that this, you have the point charge here, right? Then this one, and then here you will have the dA. So the dA has to be parallel to one another. So we will find this one in all of them. So which means that it's parallel to one another, right? So once we solve, you know, this equation, we will find that this what is called the constant, right? So the electric field and this 4 pi r square are the constant, right? So this one, the total charge over that values will be K times the total charge enclosed over R squared, right? So meaning that, for example, you can think like, you know, if you go outside, like let's think in a planet, and then you just have, you know, a particle there. So how you think the electric field will be inside if we apply these two conditions? So if we don't have anything else there, just a point.
If we just have just a point, then there.
No, it's fine. Yeah, let me explain to you.
Okay.
So in that one, you know, if we apply this constant, you know, like we will, how can I say, we will test it with this formula, right? So the total flux of E will be equal to the E surface sphere, the sum of the surface sphere times the electric field, right? And then cosine of theta, which will be 1, and then times the dA. So by condition 1, you know, we will have that the E will come out of the sum, meaning that the charge enclosed of this, you know, this charge enclosed will be 0. And then, because that one is 0, you know, we will have outside that it will have the same field. So if it is not electric field inside, same outside. So yeah,
Okay,
that is
okay.
what is tested with this.
So what you're saying is, on this one, with a single point,
Uh-huh.
if there's no electrical field on the outside, there'd be no electrical field on the inside.
Yeah.
All right,
correct.
all right. And you're
But-
using this formula here to figure that out. Okay.
Yeah, that's great. Yeah. So
Okay.
did you like it? Did you understand it?
Mostly. I would definitely need more time. And definitely probably a lot of tutoring, but because this is very much over my head, but you explained it very well.
Oh, thank you so much.
And yeah, I would love to learn more about it and even practice it more so I could better understand it. But thank you for your initial
Oh,
instruction.
wow.
I've learned so much.
Thank you so much. I really appreciate it.
Yep.
All right, classroom. Bye-bye.
Bye.